Okay, so that's about the homework one. So either you use log 10 or log, it's fine. And finally, number four, actually, in this class, I would like to help you to learn how to use computer codes to write optimization, to solve an optimization problem. Because later on, you may have larger problems and you cannot solve by hand. So I will teach you how to do it. But our classroom is right here. I think this is TR building, right? You are in TR building, no computers. So I actually book our computer lab in the E1 building, second floor. I actually book the computer lab for every Friday morning, 10 to 12. So whenever we need to have a extra lecture about the computer codes, I will let you know. So you can participate this extra programming course. And I know maybe some of you have class in the Friday morning. It's okay. I will not check the attendance on Friday morning. It's a bonus, and I will videotape everything. So if you cannot come to the computer lab, it's okay. You can always watch the video I make. But if you can come, that's a better chance for you to learn because you can uh, do the trials with me, and also you can ask me questions. So everything okay? Good? Good? Raise your hand if everything is okay. Okay, thank you. So now let's start today's lecture. Let's work on 3D Newton's method. Okay. So basically, why 3D? It's actually it's not just 3D. It's a multi-dimensional. So I should make a correction. It's not 3D. It's multi-dimensional. So it can be any number of dimension. Okay, any number. For example, I have a problem. I want to minimize f, but I have a lot of variables. X1, oops. I have x1, x2, da da da, xn. I have n variables. Okay, I have a lot of them. So this is a n dimensional problem. Okay, but we only handle one objective at this point. Okay, and of course, Newton's method cannot handle constraints, so no constraints. Okay, no constraints. So how does the derivation from the path being changed to this multi-dimensional problem? So in the past, we learned one-dimensional, now is multi-dimensional. So just like what we did earlier, any function, now I write it down as a vector. So vector x is like this, x1 up to xn. Okay? So any function f can be approximated by, again, Taylor expansion. So let me put a x0 here. But this is a expansion point. X0 vector. It is actually, it's a vector. So it's like a x1, 0, x and 0. So 0 means it's like a given point, and we don't. It's some point we chose, and we know what's the value of it. Okay, and we substitute into f to get the function value. So this is a value. When we plug in, this is a value. Okay, what's the next term? So next term is gonna be x minus x0. It's a vector. So when we do multiply for vectors, we do dot product. This is dot product. Okay. And multiply what? Multiply the gradient. So let me write this way. So what is a gradient? What is a gradient? Gradient is also a vector. Gradient is a vector. So what's a gradient? Gradient basically is partial f, partial x1, partial f, partial xn. All the first order partial derivative together, it's a gradient vector. Okay, I think you learned this in calculus. Okay, so if we go back and check Taylor expansion in the 1D case, where is Taylor expansion? Right here. So last time we did Taylor expansion. Over here, only first order derivative, and then we plug in the expansion point, right? How about this time? This time we did the gradient here, basically a lot of first order partial derivative, and we also plug in the expansion point. Okay, so after derivative, we plug in the expansion point. Okay? So that's the first order term. How about the next one? So 1/2. So over here is a little bit tricky. Because originally we should do this times, in 1D we should do this, and this is power to the second, right? But in matrix and vector form, we cannot write this way, because vector cannot be square. You cannot say square like this. You cannot do that. So what do you do? In the matrix form, it looks like this. Dot product. And then something called Hessian matrix. I will tell you what that is. And plug in x0. And then dot product. Okay? So you need to do this. Vector, dot product, Hessian matrix, and then dot product. So this is something new. I will explain in the next page. Okay, let me copy this. So there's one, we cannot do this. This is for 1D, right? This is for 1D. We should do Hessian matrix for multiple dimension. So let me copy this term right here and explain what's going on. Copy. Okay, paste. Okay, so what is this guy? Hold on. What is this guy? This is so-called the Hessian matrix. Okay, And what does Hessian matrix look like? Hessian matrix look like this. Very much like a Jacobian matrix, but different order. It's a second order function. Second derivative, a bunch of second derivative functions inside. Oops. So over here, this is a second order derivative with respect to x1. And the other one over here, also second derivative, but this should be partial x1 and partial x2. Okay. And then we have partial x1 and partial xn. Okay. How about the second row? Second row is like this. Partial x2, partial x1. And the diagonal term is second partial x2, but square right here. And dot dot dot. Partial x2, partial xn. And there are a lot of them, a lot of dot. Finally, the last one is partial xn square. This one is partial square f, partial xn, partial x1, and partial xn, partial x2. Da da da. So Hessian matrix is a huge matrix which contains all the second order derivative. Okay? So how does this look like? So every vector it's a vertical vector, right? So this is like n by 1 dot product. So from here you can tell Hessian matrix is n by n. So this is n by n, and again a dot product. So this is n by 1. But in this case, if we write it in this way, it's impossible for you to do multiplication. So in the past, we know when we say a vector A dot a vector B, that will equals to A transpose multiply B, right? This is what we learned in the past. So the shape look like this: a two vertical vector dot product, and then if you transpose the first one, become a horizontal vector, and the second one is a vertical. Then you can do multiply, right? You can multiply. So this is actually what's happening right here. Let's look at the second and the third matrix. We know when we try to multiply, we multiply one by one, right? So this is like the first one multiply the first one here, second one multiply the second one here. So we are doing this way. We multiply them and then sum them together. It's a dot product operation. So at the end, actually, this portion will give me the circle times circle plus triangle times triangle plus a lot of them. That's only the first one. How about the bottom one? Let's say here's a square, and here is a cross. And when we move on to the last one, we again move along from the left to the right, and also for the vector, it's top to the bottom. and we also do dot product. So we're doing circle times circle plus cross times triangle plus da da da, right? So this is a value, and we have n of them. So this is n by 1. At the end, this whole thing is n by 1. So we found this is a n by 1 vector. This is whole thing is a n by 1 vector. So just like two vectors are doing dot product together. So how do we operate this? So actually, the operation, the mathematical operation of this will become a transpose times the original matrix n by n and the vertical one n by 1 right here. Okay, so if you go back and take a look at the original term, let me shrink this. Resize. Okay. Too large. Okay. Okay, so if you look at the original term, basically what's happening is actually transpose and Hessian matrix and multiply. So here is a transpose. So the vertical one become horizontal. So you can do dot product. Okay? Is this clear? Is this okay? Everyone okay? Okay. So now you know this is x minus x1 dot product Hessian, all the second order derivatives, and then dot product x minus x0 again. And this is how you actually do multiplication. Okay? So let's get back to the original equation. Here is our Taylor expansion. Here's our Taylor expansion. Only the second order approximation. Second ordered Taylor expansion. Because where is the second order term? X multiply x, that becomes second order, x squared, right? Now, in Newton's method, what we want is we will do derivative. So what's happening here is that we need to do derivation, and the derivation that we do is actually operating, actually doing a gradient. Let me just do this. Because we have n variables, so you cannot just do one derivative. You need to do n derivatives, and we wish all of them become 0. So what does this mean? This means right? So for I equals to 1 to n, for each xi, when we do derivative, we wish every one of them becomes 0. This is what we wish. We wish. Okay, so let's truly do it. So how about doing derivative? So the first term, when we do derivative, let me use red color. When we do derivative, we have 0 because it's just a value, it's a constant, okay? Plus, let's do derivative, this one, okay? So what do we have in the end? Because here is a x term right here. When we do derivative, only the constant is remaining. So what we have is the remaining constant. Remaining constant right here. Okay, and if you're not sure, you can take a look. Let's take a look. So this is actually a dot product. So this is like a x1 minus x10 times partial f partial x1 and the all the expansion point plug-in plus dot 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 until the last term xn minus xn dot comma 0 times partial f partial xn and expansion point plug-in. Okay, this is basically this. The dot product actually, if you write down everything, it looks like this. And then if you do derivative, when you apply partial derivative with respect to x1, what you will have is right here. Here is your x1. So you only have this guy remaining. And no x1 for the rest. So what you will get when you do the partial derivative against x1, you only have the coefficient right here, right? And if you do partial derivative against xn, so here is your xn. What's remaining is your coefficient. Right? So if you take a look at what you have at the end, basically all together, this is your gradient vector. It's right here. Right? So I wish from here, oh, I'm dropped.